Hey everybody, it's Ripley back again. Today we're going to talk about derivatives as actual functions. So if you recall before, we could determine a derivative, this was the notation, as the limit as h went to 0 of f of a plus h, minus f of a all over h, or we could say the limit as x approached a of f of x minus f of a over x minus a. However, think about how nice it would be if instead of just being able to evaluate derivatives or slopes of lines tangent or instantaneous rates of change at points, if we could do this not just for points, but have a formula that we could use any time that we wanted. Well, there is such a thing, and it's kind of nice. It works out really, really well. What it is, if you think about it, I can't use it here because I'm going to try and figure out f primed of x, all right? This derivative as its own function, all right? You with me? So bear with, think about this. If f primed of a is produced by this formula and I want f primed of x, this implies derivative at a point, right? Deriv at a point, all right? But I want derivatives for any point. I want a formula. It's really easy. Wherever I see an a, put an x. So if I take the limit as h approaches 0 of f of x plus h minus f of x all over h. I'm done. Now, I can't use this formula anymore. This is only for a derivative at a point because you can probably see what happens. I end up with f of x minus f of x over x minus a, and that doesn't work. So I'm stuck with this guy. All right, now let's do one just real quick, just super, super quick. And then we're going to think about it for a sec. I want f of x, we're going to take the derivative of f of x equals x squared. All right, now, we're going to come up with a formula for all slopes of all lines tangent, but let's kind of wrap our brain around this graphically before we charge at it numerically and algebraically. Here's, that's terribly drawn, but you'll get the point. Here's f of x equals x squared. Now, if we're looking for slopes of lines tangent, we realize, whoops, this is y equals x squared. We realize that this thing decreases and therefore has negative slopes to the left of 0, and then it increases to the right of 0, and at 0 it levels off. So I should get a free piece of information right there. Since it levels off, what do we know that the slope of the line tangent has to be? Well, it's got to be 0. I know that everything to the left of 0 is going to be negative, so it's going to live down here. And I know everything to the right is going to be positive. Now, when I mean everything, I mean the slopes of lines tangent. I know all the slopes of lines tangent are going to be negative here because it's decreasing. And I know all the slopes of lines tangent are going to be positive over here because it's increasing. So let's do this. We're going to find f primed of x. And I'm going to make you do quite a few of these, not only just to suffer, but so that you understand the relationship between limits and derivatives, because it does pop up in some pretty weird places, not least of which is on the AP exam. So f of x plus h. So if this is f of x, this can throw students off a lot. F of x plus h is just x plus h squared, right? So this becomes x plus h squared, which is f of x plus h, minus f of x, which is x squared, all over h. Now, if I plug h equals 0 in, I get x squared minus x squared, which is 0, over 0. That doesn't work. So that tells me do some stuff. I'm going to do some stuff. Here we go. I'm going to multiply this thing out. So I get x squared plus 2xh plus h squared minus x squared all over h. Now, you can probably tell that those guys cancel, and as soon as those guys cancel, as soon as those add up to 0, look at this. I've got h's everywhere, so I can cancel an h into this guy, cancel an h into that, and make it 1. So this becomes the limit as h approaches 0 of, now notice, see what's going on here. I got 2x plus h. Now, the reason that I know that I am where I need to be limit-wise is my trouble, my 0 in the denominator, canceled. And I'm stoked, right? Now I can plug h equals 0 in, and guess what I get? I get 2x. Now, for those of you that are showing off and being all fancy because you already know the shortcut, put that away, all right? Put it away for a while. because I'm not going to let you use it, and hopefully your other instructors won't let you use it. If I sketch the graph of y equals 2x, let's see if it satisfies the things that we thought it should satisfy. This is y equals 2x, which is actually equal to the derivative of this, is actually equal to f prime of x. Well, look at it. It's negative. Now, this is where it can get a little confusing, and you're going to have to orient yourself by graph. This is really, really important. You're going to have to orient yourself by graph. You're going to have to determine whether you're looking at a function or a derivative, or you're going to get confused. Notice that 2x always increases, but we don't care about the behavior of 2x. What we care about is the fact that 2x is the derivative of x squared. So it better be consistent in terms of tangent lines, right? Lines tangent to x squared. These guys and those guys and those guys. It better be consistent with the behavior. Well, when it's decreasing, 2x is negative. When it's increasing, 2x is positive. When it levels off, 2x is 0. Now, here's the cool part, is once I know that the derivative of x squared is 2x, if, for example, I want to find the slope of lines tangent when x is 3, well, I find f prime of 3, which is just 2 times 3. It's a formula. I can use it whenever I want. If I want to know f prime at negative 4, well, this is just 2 times negative 4, because I'm just plugging values into 2x, which is equal to negative 8. Guess what? I have a function. I have a formula. Now, what we have, if we have a function, if we have formulas, then those formulas have graphs as well. So I want to do a little activity with you. It's kind of fun, and you can actually play on it because it's on the internet. I'm going to show you this. Excuse me, need a little drink of tea. All right? If we're taught, I want to make sure you understand this. Remember, graphical, numerical, algebraic. We went through sort of the numerical process of saying negative, negative, 0, positive, positive, positive. Then this is the algebraic way to come up with a derivative. Now let's talk about the graphical way. Now this is pretty cool. I want something a little, there we go. I want something that's a little nasty here. Okay, so on this, go to this website if you want to play, webspace.ship.edu. You can just, GeoGebra, calculus, derivative, blah, blah, blah. All right? Now, check this out. This black line is the function. Then we have all of these points. These points, we're going to move around to try and make a derivative, to try and see what the derivative of this would look like. All right? So let's take a gander. I have this point that corresponds to this point on the function. Bear in mind, I want to make sure you understand this. This purple curve is when we're done, and we get to check our accuracy, which is kind of fun, and we get to show the results. This purple curve is going to represent the derivative of this black curve. All right, so here we go. What do you think? That looks to be what? To be about, should we say negative 2? It's decreasing. It looks like negative 2 to me. I'm going to send it, I'm going to send it down to negative 2. That's my guess, right? I mean, it kind of looks that way. All right, now how about this point? Well, that's not quite negative. Let's see, negative 1 would look like that. It's a little steeper than that. So let's drag this guy down to a little farther than negative 1. All right, now we're not decreasing as much, are we? This line looks to be about negative 1/2. Do you agree? It's too bad that we don't have a dot here, because then it'd be easy, right? That'd be low-hanging fruit. That'd be 0. I could just slap that thing. But they don't give it to us. All right. However, now think about this. If this guy is going to be negative 1/2, I need to put this point in a place such that this part of the curve crosses the x-axis when this is 0. So I'm going to slide this. Let's see, I'm over here. Let's call that, it's not quite positive 1, it's a little less than that. And what we're wanting to do is put that in a spot. Maybe we need to move this guy up. Whoops, I don't know what that was. Maybe we need to move that guy up a little, or sorry, down a little bit. Then move this guy down a little bit maybe. And then this guy needs to correspond. I'll put it about there. That looks pretty good. Now here, what do I got? That's going to be a little bit bigger than 1, isn't it? We'll move it up a little bit. And we'll tweak this thing if we need to. Then this point corresponding, what do you think? That's, well, I don't know. We'll move this guy down a little bit, and I'm going to move that up a little above 1. This is going to be ugly. We'll tweak it when we need to. All right, now here's where the black curve levels off. Isn't quite there, right? We're still a little bit positive because we're still increasing just a little bit. But I'm going to move this thing just a titch up. Now I realize that this is pretty ugly, and we're gonna tweak this down after we sort of get a stick figure of what this looks like. Now this is negative. What do you think? Maybe is it -1? I don't know. Yeah, maybe -1, close to -1. We'll move it down a little bit farther. About there. Sound good? Now this guy right here, we're back to sort of a steep part. That's what should we call it, -2, and if we have to tweak it, we'll tweak it. Yeah, like that, right? So we get sort of a pretty little thing going on here. This is where it appears to be much steeper, so I'm going to move that a little bit farther down here. We're still decreasing here, but not as much. We'll call that -1-ish. This, it leveled off here. If I had a dot on here that corresponded to this leveling off, it would be exactly at 0, but we're just, this kind of looks like it where it needs to be, right? Maybe a little bit higher, I don't know. And then this is the steepest part. We'll call this, I don't know, you think that that's steeper than 1, maybe we'll put this thing up about here. It's pretty high, pretty high. Okay, so I'm going to tweak this just a little bit just to make it pretty because I have ego in this and I don't want to screw it up. I don't know. Do you guys think? That looks pretty good, doesn't it? Maybe move that down a little bit. All right, so let's check. Let's be sure. When the black curve is decreasing, the purple curve is negative. You may say, but Ripley, it's increasing. I don't care if it's increasing. I care about its sign. I don't care about its behavior. That's a little disingenuous for me to say that because I do care about its behavior. But most importantly, right now, we need to get our brain wrapped around the fact that I care about its sign. Black curve decrease, purple curve negative. Black curve increase, purple curve positive. Black curve decrease, negative. Increase, positive. We need to move this a little bit, don't we? Because there's a 0 there. Maybe move this up a little bit. I think that might, there we go. Maybe move it up just a titch, right? And move this guy up a little bit, like right there. Okay? Now, the other thing that's really important is that our zeros on the derivative correspond to levelings off. When this guy levels off, that has an x-intercept. When this guy levels off, it has an x-intercept. When this guy levels off, it has an x-intercept. We're not worried about when this thing levels off. We'll worry about that down the road when we start taking multiple derivatives, which is what we'll talk about. But for the purposes of this little app, we're not worried about that. All right, let's check our accuracy. Let's see how we did. You ready? I'm so nervous. Check accuracy. Ooh, 84. Bummer. Let's show the result. Yeah. Huh? Wow, look at that. Well, I guess this... maybe. I mean, we were pretty close. Let's see. If I move this guy down here, I would have been much happier. Yeah, I was off a little bit. Let's check, though. Yeah, I mean, I was pretty close before. This was a little too high. Anyway, you see how this works. Okay? I think that's a great demo. This is definitely a very cool little app that you can go in and play with when you're trying to figure out what the behavior of the derivatives are when compared to the behavior of the function itself. Okay, we need notation. We need language. Mathematics is about language, all right? And we need to be able to speak the language of math, all right? So let me change to black because this is a big deal. Our first notation that we learned is f primed of x when we're talking about a derivative of a function as a function. Another notation that is used commonly is y prime. Now there's something called Leibniz notation, which is really important because it's going to show up from now until the day you stop doing calculus. Leibniz notation looks like this. What I do is I do d over dx of y. What this means is this literally means take the derivative of y with respect to x. What it's saying is take the derivative with respect to x of what? Of y. It's kind of in that f of x notation. However, typesetters don't want to have a bunch of parentheses, especially back in the day when they had to actually set type by hand, and setting type cost money because it took up space. So we shrink this to dy over dx. All right, these are the three most common ways to denote a derivative of f of x. All right, y prime, f prime of x, dy over dx. Now, while we're here, let's go ahead and talk about higher derivatives. A second derivative. Now I call this f double primed of x. This would be y double primed of x. Now this is important. I'm going to put in this intermediate step, even though the notation isn't used a whole lot, but it'll explain why we get what we get. Now we are taking the derivative of the derivative. And what that turns into algebraically is d2y over dx squared. Now you may think, well, wait, Ripley, why don't I have parentheses over this? You yell at me all the time about if I'm going to square something, I need to put parentheses around it. No, it's true, I do, no doubt about it. But again, we don't want too many parentheses, but particularly typesetters. All right? Now, what's really important here is that you understand that Leibniz notation is actually an algebraic construct based on slope, which means we can divide this thing up, which you will do a bunch in the future. We'll do it in this class. This is algebraically separable, so I can move the dx away. In other words, if I say set this equal to 2, I could say that dy equal to dx, which is pretty helpful. Okay? Now, higher order derivatives, let's keep talking, would be like a third derivative of x. Typically, you would write this, because this gets ridiculous if I want the sixth derivative, right? Because I'd be f 1, 2, 3, 4, 5, 6 x. It's ridiculous. So what we would often see a third derivative or higher written as f, then parentheses 3 of x. You'll also see this as y 1, 2, 3, or you will see this as d3y over dx cubed. The most common notation for super high order derivatives are this. Now you may ask, why am I taking multiple derivatives again? Well, that's a pretty easy question to answer. Let's start with what we started this whole discussion about as position and then velocity, right? The derivative of position is velocity. So if I have the position function represented by s of t, I know that s primed of t is the derivative of s of t, and I know that this is equal to the velocity. I know that s double primed of t is equal to the first derivative of velocity is equal to the acceleration, right? The instantaneous rate of change of position is velocity. The instantaneous rate of change of velocity is acceleration. If I want to take even higher order derivatives, like if I want to take the third derivative, that would be the second derivative of velocity and the first derivative of acceleration. And what I get is referred to as jerk. Jerk. Likewise, if I want to take even more derivatives, now you may say, whoa, what? Wait, what's this jerk? Well, think about why they call it jerk. The instantaneous rate of change of acceleration, think if you're in a car and somebody punches it, what happens? I change the acceleration. So I start hitting the gas, and then I punch it. What does your head do? It jerks back. I'm on the brakes, and all of a sudden I step on the brakes. What does your head do? What does your body do? It jerks. So the instantaneous rate of change of acceleration is jerk. Once we take another derivative, we start getting into the quantum area. All right? We can't talk about Newtonian ideas about derivatives. We get into what's called, which is pretty funny, if I take the derivative of jerk, I get something called snap. If I take the derivative of snap, I get something called, you guessed it, crackle. Oh, physicists, they're so funny. If I take the derivative of crackle, I get something called pop. Okay? All right. So those are the higher order derivatives of the position function. But at the end of the day, we need to be able to take as many derivatives as we need to, right? As we want to. So we have to have this notation by which we can do it. The most commonly used, the most common that you're going to see are going to be these three. But the one that has the most utility algebraically is the Leibniz notation. A guy by the name of Leibniz. You've probably heard of him before because he's the other guy that's credited with inventing the calculus. Okay, bell's going to ring here in just a sec where I'm recording. So I'm going to end this section of the video, and I'll meet you guys back here on the next page here in just a sec, where we'll talk about some other issues around. Okay, sorry about that. When the bell goes off, all hell breaks loose in my classroom. So, all right, really quickly, I want to talk about the idea of differentiability. All right, when we say differentiability, when we say, differentiability, when we say that f is differentiable, and I'm going to be lazy, diffable, at x equals a, this implies that f prime at a exists. And you may say, wait a second, what does it mean for a function to have a derivative that doesn't exist? Well, let's look at that graphically. There's a couple of ways. First things first, let's go to our go-to guy, which is 1 over x. So I know what 1 over x looks like. It looks like this, and it looks like this. Clearly, there can't be a derivative at x equals 0. So f prime of 0 does not exist because the function itself doesn't live there. So that would be a point of discontinuity, right? Of non-differentiability. Which the question is can I take a derivative of a continuous function, of every continuous function everywhere? Well, go away. No, don't you dare restart. What if f of x, I'll be so annoyed, is equal to absolute value of x? Well, let's look at that. So absolute value of x looks like this, right? Now, I'm going to be able to take a derivative. This is just a line. We know what this guy looks like, right? This is negative x when x is less than 0, and x when x is greater than or equal, when x is greater than or equal to 0, right? So I would have a derivative of negative 1 to the left and a derivative of positive 1 to the right, right? Because it's just the slope of those lines. Remember, derivatives are just slopes at the end of the day. So the derivative of every line is just its slope. I mean, that should be relatively obvious at this point. However, at 0, here's the problem. If you look at 0 as a spike or a cusp, then where do you hang your derivative? Well, is it here? Is that going to be the one that describes the behavior of the curve? Is it here? Heck, is it negative 1? Is it positive 1? Well, if you think about what a function is, if I plug in a value, if I'm trying to figure out f prime of 0, then what I will get is more than one value. I could say it's negative 1, question mark, positive 1, question mark. Well, if I've got that, I don't have a function. So it would not be differentiable at x equals 0, okay? Hopefully that makes sense. So places where I get places of non-differentiability are places where I lose continuity, where I have a point or a cusp, right? Those are, you got to look out for those, because if I can't take a derivative at a value, oh heck, sort of breaks loose. Also any place where, like, if f of x equals the square root of x, clearly I can't find f prime of negative 6. There's no way, because I know that the function doesn't even live over there. So any place where the function isn't defined, I guess that would be true of 1 over x at 0 as well. All right, if we say f is just differentiable, this implies f prime of x exists everywhere. Or, now we got to be careful with this notation. I'm being a little bit glib here. And then I'll say it parenthetically. At least on the domain, right? So for example, 1 over x is differentiable everywhere its domain lives. I can take the derivative anywhere except at 0, all right? Except at 0. So I say that f of x equals 1 over x is differentiable for all values except x equals 0. Okay, so be a little bit careful here. You can talk about being differentiable on an interval, which means its derivative the derivative exists everywhere on the interval. Now, this idea of continuity, this is the last thing I want to talk about in this section, and then we'll be done. This idea of continuity kind of brings into question, like, how does this thing work? We started with limits, and then we moved on to continuity, and now we're talking about differentiability. I'm just going to leave it like that because I don't want to have to write out differentiability because I'm lazy. Now, let's think about this. If the limit existed, did that imply continuity? No, right? Because I could have a function that went whoop, open, whoop. This is clearly not a continuous function. However, the limit exists at x equals a. If I'm continuous, does that imply that I'm differentiable? Well, no, because absolute x is continuous, but not differentiable at x equals 0. That doesn't work. All right. However, we do know that the converses of these are true. We know that if we were continuous, then a limit existed everywhere, so long as I was continuous. Likewise, there's a theorem, and that theorem says if f is diffable, that implies f is continuous, which implies, if you think about it, if it's continuous, this implies that f has a limit everywhere. There's no, go away. There's no way, let's see, everywhere, I spell everywhere, everywhere. All right, that's a, well, this is the Ripley add-on theorem. If f is differentiable, then it's continuous. If f is continuous, then it has a limit everywhere. But I cannot run the converses of those and have them be correct. Okay? In other words, limit does not imply continuity. Continuity does not necessarily, limit doesn't necessarily imply continuity. Continuity doesn't necessarily imply differentiability. But the converse, the other way around, is definitely true. If I'm differentiable, this implies continuity. If I'm continuous, that implies limit exists everywhere. Okay, that's enough of me yapping at you. Hopefully that was helpful. This is a super intense, well, it's not intense, it's actually fun. This is probably the most fun section, I think, out of the introduction to differential calculus. What you're going to have to get your brain wrapped around is the relationship between graphs. That's really, really key. And in my class, if you're taking my brick and mortar class, I'm going to harp on the idea of orient yourself by graph. What graph are you looking at? Are you looking at a function? Are you looking at a derivative? Are you looking at a second derivative? And what does that tell us? Okay? So I'll let you guys go. Have a wonderful day, and I'll see you in the next section.